students. Today is 24th of May. Okay, so it's, let's start by saying Viva el Ecuador. Okay, today is 200 years of our independence. So let's be happy and let's live up to that. Okay, somebody put their lives so that we get independence. So it's worth to know it, to remember. So let's everybody make an effort in order to compensate them, to emulate them. Okay. Okay, people. I asked you to review some concepts for this class. So in order to check who has done that, I'm going to give you a very, very short test. It's a 10-minute test, but I should call it a quiz, okay? But this is not worth any points. So I'm not going to take any points off if you do not complete it, okay? So it will be available to you at 7 and 10. So in a couple of minutes. So you have to go to Aula Virtual. You have to go to Aula Virtual, and there is an evaluation. And it has 4 questions. It's a multiple choice questions. So yeah. And as I said before, it's not worth any point. So if you do not complete it, I just want to know if you review, if you prepared for this session. That's all. Okay. So in about 1 minute, that will be available to you. As I asked you yesterday or on Friday, please, if possible, try to change the name with which you are recognized, okay? And try to start by your last name, okay? So when it appears to me here on the right-hand side, I will have the list in alphabetical order, okay? So if possible, try to change the name with which you are recognized. So start by your last name and then comma, and your first name, if possible, of course.
Excuse me, doctor. What's the access code for test?
SS. Ship structure. The access code is SS. I'm going to put it in the chat with capital letters. Please, it's big. Big S, big double S. I just write it in the chat. So it's double S. For those of you who got late, please go to Aula Virtual and you have to complete a quiz, independence quiz. in 10 minutes. It's just 4 questions about the deduction of the equation for the bending moment as function of the curvature. That's all. Got 10 minutes for that. Well, 8. For those of you who came late, you have to go to Aula Virtual and complete the evaluation, the quiz, short quiz that we are completing. Okay, it's just a 4-question, multiple choice quiz, something very light, okay? Very. Somebody asked me for the password. It's in the chat. Come on, people. Can you read? Can you read? Today is 24th of May. Come on. Those of you who came late, you have to go to Aula Virtual and do the quiz. It's a short quiz, 4 questions, multiple choice. The password is in the chat. Password is in the chat. Okay, let's make a quick review. I'm sorry about I didn't have all the characters for write the questions, but I guess we can understand what I was saying. Okay, so the first question is, if we have this figure here, how did you express the strain? Anybody? The first one? Let me share the screen. Let me share the screen so we can talk on something here. Okay, so can you see my screen? Anybody?
Yes, doctor.
Yes, doctor.
Thank you. I got problems with, I have a very small screen now. That's a problem. Okay, so this review was about kinematic hypotheses, and this is what I'm trying to show here in this figure. Okay, so the strain, one of the ways we have to write the strain is that epsilon x, that's the strain, is equal to what? Minus y times d theta. Okay, and the thing here is that we have this deformed situation. Okay, this was the original one. That's the original one. So what we do is we draw a parallel to this in here. Okay, so this angle is d theta, and that angle is the same as this one. So if we are here, this is du. So du is equal to I d theta. Okay, any questions about these, people? Anybody? Are you with me, people, or are we having a?
Doctor, I have a question.
Go on.
Why is the sign and the strain
Negative.
negative?
That's a good question. The thing is this. Let me erase this. This is not worth anything. This is just okay. The thing is this. Okay, everything here is positive. This is. I think we need. Okay, let me answer this question. Okay, you see that to the right, this is x positive. Upward is positive, right? And most importantly, the bending moment, okay, which we do not yet relate it, is like that. Okay, it's positive like this. Remember, this is positive side, negative side, and this is positive and positive. If you apply a positive bending moment, this is the way the beam is going to deform. Okay, and you see that with everything positive, this is the way the system is going to deform. So this is the U. And you see that the length, the original length, which is from here to there, this is the original length, has reduced. Now the length right now is this one. So it is reduced. So with everything positive, you have a reduction in length. That's why we need a negative sign. I don't know who asked the question. I don't know who asked the question, if I answered the problem. Person who asked the question, please. Did I answer your concern? I'm seeing that there is an error here. It's du, it's minus y d theta. And epsilon x, it's du dx. So this is wrong. This is not correct. This is, so that means that if we divide this by x, by dx, we got, this is d theta dx. This is correct. This is not correct. But yeah, we need a negative sign. Now, one thing which is very important is that we see that this angle, this theta, can change sign. So in this way, when you have this type of deformation, the angle is positive. That means that when it's concave, looking downwards, the d theta is going to be negative. Okay, so we have to be careful with that. Okay. Now, next question is about what? What the exact expression for the radius of curvature? Okay. And here, I don't know if, did you have problems with the symbology that I employed? Okay. Oh, Jesus. See, the thing is this. Thing is this, okay? This is rho, and this is what I wrote like this. This is used to be density. Here is the radius of curvature. Okay. Now the radius of curvature exactly is this. So 1 over rho is exactly equal to the second derivative of the function and divided by 1 plus b comma x to the 3/2. That's exact, okay? But what we do is we assume that v comma x, that's the slope, is small, okay? Now, if we assume that, then if this is small, okay, we can say that v comma x 3/2 is neglectable. If this is true, then 1 over rho is going to be v comma xx. And people, See, this is the second derivative, b with respect to x squared. Now, this expression here has units of, in the numerator, of length, in the denominator of length squared. So it's 1 over length, and this is 1 over length. You have to be careful because remember, we have to check all the time the units, okay? So that was this is the exact expression for the curvature. And I got lost here. The third question is the normal stress in beam bending. The normal stress in beam bending. Okay, and now this is just an application that you have to review Hooke's law. When we have only sigma x, any other of the components of the stress tensor is different than 0. Only sigma x is different than 0. Then we can say that sigma x is simply E epsilon x. Right? And if we assume, this is Hooke's law that you have to review. Now, if you replace this, okay, using the second, this approximation, okay, and this is equal to minus y v comma xx. So sigma x is going to be equal to E minus that. This is an approximation because this is just an approximation. So this is not exactly. This is exact. This is exact. But the problem with this is that this is a nonlinear relationship. If we try to reduce this into here, then the solution process is going to be very difficult. That's why we prefer just to simplify. Okay? So that's a simplification, but it's quite useful. It's very useful expression. And finally, the last question was, what's the, oh man, trouble here because I cannot see this. Okay. What's the expression for the bending moment? Okay. And here we can say that if we have, this is X, this is Y, this is the bending moment. So here I have a distribution, or assume, this is an assumption because it comes from the kinematic hypothesis and it comes from the Hooke's law and also using this approximation. So all of these assumptions, okay, gets up to this. So this is assumption. But we have to be certain that this has to be consistent with this value. Because remember, this comes from equilibrium. So why we are making a cut here? So all of this part has to be in equilibrium. And for this to be in equilibrium, we need to have this exactly the value of the bending moment. So what we do is we integrate. I'm not going to do it. This is something that you have to do. Minus sigma x y dA. So this negative comes from the fact that in the upper part, the positive side, a positive stress causes a negative bending moment. That's why we need this negative. And if you replace this into here, you can say that mz of x, this is the bending moment, is equal to E I sub c v comma xx. Okay, so as I said before, okay, here we're assuming that this curvature is positive. And in this case, this is basically the curvature, an approximation because we are neglecting this term. So this is the curvature. And the positive curvature is related or is caused by a positive bending moment. So this is the curvature, which is by definition 1 over rho. See, 1 over rho is this. So this is a curvature. And this is the bending moment. So we're saying is that positive bending moment generates positive curvature. So that means that you are like this, smiling. Okay? So if you want to be consistent, that's why we need the negative side in here. Is there any questions about these short questions that we just prepared? People, any questions? Any questions about this? No? The problem is I have many things open here, so I'm lost. Let me close this. Okay, Mr. Benavides, how was it? Was it too easy for you or what? Mr. Benavides?
Good morning, doctor. And I think that I just want to prepare better because
Okay.
and at the beginning I have small confused with the signs because I didn't understand good. Then in the second one, I understand better.
Okay, the problem is that I don't have all these characters. See, I had to write rho, I had to grab theta, but the problem is that I don't have the characters here to prepare this quiz. But anyway, the idea is that make you awake, okay? You have to review before the class. That's the message, okay? Mr. Tenemea, how did you do? Did you do well or what? Mr. Tenemea?
Yes,
How did you do?
well, for this.
Evaluation. Good. Okay, where are you right now, Mr. Tenemea?
What?
Where are you right now?
Doctor, I don't understand.
Where
Sorry.
are you? Where are you? In what city you are right now?
In Cuenca.
Okay,
I
good.
live in Cuenca.
Okay, good. Miss Valdez, how did you do in this evaluation? 4 by 4?
Not too well. I have to read more about this.
Come on. Well, this is something which is very
There's
important.
more.
Okay, this is something that you mentioned, Ms. Valdez. In the evaluations, okay, the people, this is for everybody. The first thing that you have to do is read. I would say it one more time. You have to read. If you do not understand the question, don't start writing. Wait, read it again. And only when you understand the question, then you start, okay, this is what I need to do, start analyzing and all of that. And finally, you start answering. So those are the 3 steps. But the first thing that you have to do is understand the question. And yes, I have to recognize that we have these problems with the symbology that I'm limited, okay? But yeah, you have to read. Okay, if there is no more question, then some reason, I don't know what is. Okay, people, I need one fresh, Can you see my screen? Can you see my screen, anybody?
Yes, doctor.
Yes, doctor.
Yes, doctor.
Okay. So I have to write to the left because I don't know, I cannot erase that. Let me see if I can erase this thing. Anyway, so here on the left, okay. we have two relations. First, we have something from equilibrium. From equilibrium. And the equation is the second derivative of the bending moment with respect to x is equal to p of x. This is inside the domain. Okay, so it is between 0 and L. And now we said that kinematic hypothesis combined with Hooke and also simplifying the curvature. Using these three considerations or assumptions or simplifications, we said that the bending moment could be expressed as E I sub c v comma xx. Now, what we do now is we replace this into here. Now, we have to be very careful, people, because if we use only the equilibrium equation, we only are able to solve statically determinate problems. And the problem is that there are many indeterminate problems. And that's why we have to include these other assumptions. It's like including in our analysis more equations in order to solve for the unknowns. Okay, now after we replace this into here, we know that we have the second derivative with respect to x of e I sub c p comma xx. Okay, now usually the Young modulus is constant because it's a single material, but the sectional inertia is possible that it changes, right? For example, in the case of the ship, okay, of course, the inertia, the sectional inertia at the bow, the section will be something like this. And at midship, it will be something like this. So the sectional inertia will change. But what we do is we consider that for prismatic beams, so we consider that the section is uniform. So this is not the case. So if this is the case, then the inertia is also constant. Not only E, but also I sub c is constant. And we can say that the result is going to be this. So this equation this is the beam equation. It's not only equilibrium, but there is something extra there. And this something extra allows us to solve not only determinate problems, but also indeterminate problems. Okay, people? Now, before we go on, here, this is a fourth order equation. This is fourth order equation for V of x. Okay, so if it is a fourth order equation, that means that we need 4 boundary conditions because we have to integrate 4 times, okay, for V of x. The problem is that every time we integrate, we include a constant of integration. If we integrate 4, that means that we need 4 boundary conditions, okay? Now, one of the boundary conditions at least has to be a value of V, okay? And at least one boundary condition has to be a value of the slope. Otherwise, we wouldn't be able to solve for all the boundary conditions, for all the constant of integrations, okay? This is something which is very important, okay? So I'm going to insist in the next slide. So we need 4 boundary conditions. This is a linear equation, okay? you see that you have here V, and this is not multiplied by itself. E sub I sub C is constant because in this case we're considering prismatic beams. Okay, and this is usually it's non-homogeneous problem. That means that V identically equal to 0 is not possible here because the problem is not homogeneous. Okay, but this is very important for us right now, boundary conditions. We need 4 of them because this is a 4th order differential equation. Now, Jesus, I don't know what happened with this. Let me stop this because I don't know what happened with this. Just a second, please. Just a second. Can you see my slide? Can you see my full screen slide? People?
No, doctor.
Yes?
No,
Yes or no?
No.
No?
No.
Okay, let me. See, today is Monday. Yeah, I know it's Monday. How about now? Can you see it now?
Yes, doctor.
Okay,
Yes,
good. Okay, see here, about the boundary conditions, remember that we need 4 of them, okay? And here, these are the classical supports, simple, clamped or fixed, guided or free end, okay? Now, here, I have separated, okay? In this column, in the second column, we are saying something about displacement, okay? So this is about displacement. And here, in this column, I have something about rotation. So you see that for every type of support, when you say something about the boundary condition, you have one condition related to displacement and the other condition is related to the rotation. For example, in the simple support, there is no vertical displacement and the bending moment is 0. Bending moment is related to rotation. In the case of the clamped case, okay, there is no displacement, there is no rotation. In the case of the guided end, okay, there is no opposition to vertical translation. That means that the shear force is 0. Okay, so we have something related to displacement, force, and there is no rotation. Okay, and finally, in the case of the free end, it can move vertically, it can rotate. That means that there is no shear force, there is no bending moment. Okay, all of this is hopefully it's good for you. Please, in every case, we have something about the displacement, something about the rotation. Okay, in no way you can have both. For example, you cannot specify simultaneously the vertical displacement and the shear force in an end. You cannot specify, okay? If we could have time, I could explain why, but it's something that you have to keep in your mind, okay? If you specify the rotation, you cannot specify the bending moment. The other way is true also. If you specify the bending moment, you cannot specify the rotation, okay? So, but you need 2 in every support. So you specify 2 boundary conditions in one end, 2 boundary conditions in the other. So you have the 4 boundary conditions that you need to solve any beam problem, okay, because you need 4 boundary conditions, okay? Now, in some cases, we have these springs, okay? For example, here. Now, in general, we are considering that in the vertical direction, okay, we have the positive displacement. Okay, so if you consider a vertical positive displacement, okay, I'm saying that the positive is upward, okay, the force from the spring will be downward. So the force will be K, the constant of the spring, times the displacement at that point. But please, it's the opposite to the displacement. Similarly, if you have, in some cases, you have rotational springs, okay, in that case, the moment generated will be opposite to the rotation. And finally, it is possible, in the last session, we did an example considering a moment, an external moment applied on one end, okay? And my suggestion in those cases is to do a short analysis like this one here, okay? In this case, let's suppose I have a force downwards, I'm sorry, okay? So this is X, and you see that this is the end, the left end. So this is X equal to 0. So if we need to take a boundary condition here, what I do is I make a cut very close to the end, very close. Question, Mr. Nieto, in this cut, the shear force is positive upward or downward? Mr. Nieto, here.
It's positive.
Yeah, but my question is, if it is positive, points upward or downward? You don't remember?
Repeat, please, Doctor.
No, I'm not going to repeat. Mr. Guaman, in this cut, the shear force is positive upward or downward? Mr. Guaman?
Upward.
In this cut, no, Mr. Gomez, in this cut, the shear force is positive upward or downward?
Upward.
Upward, yes. Remember, this is a positive phase. Okay, so this is a positive phase. This is a positive bending shear force. Remember, when you do not something, assume it as positive. So this is V at 0. So this little piece at the end has to be in equilibrium. So what we have is minus the force P plus the shear force. I don't know if this is correct or not. So that's why I assume it as positive. There has to be equal to 0. That means that V at 0 is equal to P. And this is a condition. Because the shear force, I'm going to write it on the left because I have more space. The shear force is minus E I sub C, the third derivative. And this is equal to P. And this is your condition because you are saying something about the third derivative of the function that you're trying to determine. So this is a condition. So P is something that you know because this is a known value. E I sub C is also known. So the third derivative has to have a specific value. That's condition. That's condition. Okay? Any questions about these people? If you don't have a good memory, my suggestion is try to practice. See, get a piece of paper and write the boundary conditions for each one of these supports. If you do not apply the correct boundary conditions, you're simply solving another problem. Yeah, and if I give you a quiz, if you do not set the correct boundary conditions. There's nothing I can do. So please practice, okay? Get a piece of paper, write the boundary conditions, and that's it. Okay, now let's do a couple of examples. Okay, let's consider a clamp beam with a concentrated force. So this is the example that I'm going to consider. So it's clamped on the left, clamped on the right. We have a beam. You see that it is prismatic, and we have a concentrated force here. Let's put it downwards. So this is X, this is Y. Okay? And the position where the force is applied is X equal A. The length of the beam is L. Okay, so in this case, first thing that we have to determine is this a determinate beam or indeterminate beam? Mr. Ortega, Andres Ortega, what do you say? Is it determinate or indeterminate beam?
Indeterminate, doctor.
How many, doctor, please, don't call me doc. What are the reactions that we need to determine? How many? How many reactions? How many?
2 reactions.
No. If you have 2 reactions, then this would be a determinate case. Miss Aviles, how many reactions do we need to determine in this case?
And we're on me, doctor. And we have 2 reactions in the fixed support.
How many?
And in a moment.
How many?
We have 1 reaction, for example, if the first fixed support is 8 points, we have a force in Y,
Okay.
a force in X, and a moment.
Yeah, but the problem is this, people. Usually, you have to be careful because when you see in this case, there is no forces in the X direction. So we don't need to include forces in the X direction. Okay, so as you said, this is R sub A. So we assume it is in the vertical direction. And we need a bending moment in the Z direction. Right, that's 2. And in the other end, we also have RBY and MBZ. So that's 4. So that means that this is an indeterminate case. If it's an indeterminate case, people, the only way that we have to solve is to include or to consider to solve the full bending equation, not equilibrium. So this is what we have to solve. This has to be solved. This has to be satisfied in every point, in every element inside the beam. That's what we're saying. If we solve this, we are saying that we consider any arbitrary element, and that arbitrary element is in equilibrium. Okay? We need boundary conditions. So an X equals 0. Miss Arechua, what are the boundary conditions for this case? In X equal to 0.
Excuse me?
What are the boundary conditions at X equal to 0?
The sum of the force, it's equal to 0.
No. It's a clamped case. Mr. Cedeño, Mr. Jarry Cedeño, what are the boundary conditions on X equal to 0?
Slope equal to 0.
Okay, and
Shear force equal to 0.
No, come on, people. Miss Flores, Alison Flores, Other boundary conditions at x equal to 0 is clamped end.
Good morning, doctor. In displacement, B is equal to 0. On the rotation, the first derivative is 0.
Yeah, similar for x equal to L, right? So the displacement on the right end is also 0 and also the rotation. So this is it. And finally, before we go to the break, Miss Sigüenza, would you please tell me what P of x is? P of x. Sigüenza, are you there? No? Okay, let's, oh, you're here. Go on. Sigüenza, are you there? No? Mr. Soria, tell me, what is P of x? Mr. Soria?
Yes, doctor. Px.
What is P of x, Mr. Soria? What is P of x? P of x. What is P of x? Let's write it here. What is it? What is
The function of the
what?
force. Of the
Force? No, it's not complete that this explanation. I need something extra, Mr. Soria. It's force, Mr. Pesantes, force.
Sigma x minus
No. Please.
delta function.
No. My question is, what is P of x?
Force per unit length.
Exactly. It's a distribution of force per unit length. Okay. So after if we know what P of x is, then we can go on. It's a distribution. Now tell me, what is it? Mr. Llanos, tell me, what is P of x in this case?
Good morning, doctor. P of x is minus f times x minus 8.
Delta.
Sorry, not delta.
There. Now, people, this is the most important part of the solution process. Okay? If you have established this correctly, the rest of the procedure is just going back to calculus. This is structures. Okay? Now, be careful here. Okay? As you can see here, this is one boundary condition on displacement, one boundary condition on rotation, one boundary condition on displacement, one boundary condition on displacement. So the boundary conditions are correct. If this is correct, that means that the solution is unique. And this has unit of force, 1 over L. So this is force per unit length. That's all the forces that you have. So this is correctly a proposed problem. Now, from now, what you have to do is you have to be careful in solving this problem. Now, let's take a break, and when we return, we can go on with the solution, okay? Let's take a break. Isaac, would you please stop